Welcome, my friend, to this quiet moment, as the day gently recedes and stillness begins to settle around us. Tonight, we'll embark on a serene journey into the heart of the universe, exploring a concept that underpins all of existence, yet often feels wonderfully, profoundly mysterious: the quantum. Let your mind drift softly, as we contemplate the very fabric of reality, not with the urgency of understanding, but with the gentle curiosity of a dream. Imagine for a moment that everything you perceive as smooth, continuous, and infinitely divisible is, at its deepest core, actually made up of tiny, indivisible packets. Like a beach that appears as a vast, seamless expanse of sand from a distance, but up close, reveals itself as countless individual grains. This profound idea is at the heart of quantum physics. A quantum is, quite simply, the smallest possible amount of any physical entity, any property that's involved in an interaction. It's the universe's fundamental, irreducible unit for a particular quality. Think of it as the ultimate indivisible coin in the cosmic currency of energy and matter. You can have one, or two, or three, but never 1.5. This fundamental notion that a property can be quantized, meaning it can only exist in these discrete, distinct steps, is called the hypothesis of quantization. It means that the magnitude of any given physical property isn't a continuous spectrum, like the smooth glide of a ramp. Instead, it's more like a staircase, where you can only stand on individual steps, not anywhere in between. These steps are always integer multiples of one basic quantum. So if a quantum of energy is, let's say, a unit of 1, then you can have 1 unit, 2 units, 3 units, but never, ever, 2.5 units. It's a profound departure from our everyday intuition, where we assume we can always subdivide things further and further. Consider light, for instance. We experience light as a continuous flow, a smooth wave of energy. But at its most fundamental level, light itself is quantized. A photon is a single quantum of light. It's an indivisible packet of electromagnetic radiation, carrying a specific frequency and energy. When light interacts with something, it doesn't do so partially. It's either a whole photon, or no photon at all. It's like turning on a faucet, but instead of a continuous stream, what comes out are individual, distinct droplets, each one a perfect, complete unit of water. Each photon carries its own unique energy fingerprint, determined by its color or frequency. And this energy can only exist in these specific, discrete amounts. There's no such thing as half a photon or a quarter photon when it comes to interaction. It's a complete, singular entity. This principle extends far beyond light. Imagine an electron, a tiny, fundamental particle, gracefully orbiting the nucleus of an atom. In our classical understanding, we might imagine it could orbit at any distance, with any amount of energy, like a satellite in orbit around a planet, able to adjust its altitude smoothly. But quantum mechanics tells us something profoundly different. The energy of an electron bound within an atom is also quantized. It can only exist in certain, very specific, discrete values, corresponding to distinct energy levels, or shells, around the atom's nucleus. Think of an atom as a tiny, intricate musical instrument. The electrons within it can only play certain specific notes, certain energy levels, and cannot linger in the spaces between these notes. This is why atoms, and indeed all matter, are stable. If electrons could lose energy continuously, they would spiral inwards and eventually crash into the nucleus, making atoms inherently unstable. The universe as we know it would simply collapse in an instant. But because electrons are constrained to these quantized energy levels, they can only jump between them, emitting or absorbing a precise quantum of energy, often a photon, Wh. And they do so. This elegant dance of quantized energy levels ensures the stability and structure of all the matter that surrounds us, from the air we breathe to the stars that twinkle above. It's a delicate balance, orchestrated by the quantum rules of engagement. This idea of quantization is not just an isolated phenomenon, it's one of the very cornerstones of the much broader and more profound physics of quantum mechanics. It's a framework that fundamentally reshapes our understanding of reality at its most minuscule scales. The quantization of energy, and its profound influence on how energy and matter interact, a field beautifully described by quantum electrodynamics, forms an essential part of the fundamental blueprint for understanding and describing nature itself. It whispers to us that the universe, far from being a smooth, flowing continuum at all scales, is instead built upon a foundation of irreducible units, like a digital symphony composed of individual, distinct notes. Now, let us turn our gaze to the historical threads that wove together this incredible understanding. The modern concept of the quantum in physics didn't just appear fully formed, it emerged from the brilliant minds wrestling with perplexing problems. Its origin story leads us to a specific date, a precise moment that altered the course of scientific thought, December 14, 1900. On this day, in Berlin, a brilliant physicist named Max Planck presented his findings to the German Physical Society. He stood at the precipice of a revolution, though he might not have fully realized its monumental implications at the time. Planck was grappling with a long-standing, stubborn problem in physics known as the blackbody radiation problem. Imagine a perfect absorber and emitter of radiation, a theoretical black body. When heated, it glows, emitting light across a spectrum of frequencies. Classical physics, using well-established laws, predicted that a blackbody should emit an infinite amount of energy at higher frequencies, like ultraviolet light, a theoretical catastrophe famously dubbed the ultraviolet catastrophe. This prediction simply did not match experimental observations. Nature wasn't behaving as classical physics expected. The discrepancy was a thorn in the side of physicists, a puzzle that resisted all attempts at a classical explanation. Planck, in his genius, was searching for a way to bring theory into agreement with experiment. He didn't initially set out to invent a new physics, but rather to find a mathematical trick that would solve this specific problem. What he discovered, however, was far more radical. He showed that if he modeled the harmonic oscillators, the tiny, vibrating entities within the blackbody that were responsible for emitting radiation, as having discrete energy levels, the theoretical predictions suddenly aligned perfectly with the experimental results. Instead of being able to vibrate at any energy, these oscillators could only vibrate at specific, quantized energies. It was a bold, almost desperate, postulate, but it worked. It solved the ultraviolet catastrophe, making the theoretical curve perfectly match the observed reality. In his groundbreaking report that day, Planck didn't quite use the term quantum in the exact way we understand it today. Language, like understanding, evolves. Instead, he used the term elementar quantum to refer to what he called the quantum of electricity, which we now know as the elementary charge, the fundamental unit of electrical charge carried by a single proton or electron. For the smallest unit of energy itself, he employed the term energy element, or energy element, rather than calling it a quantum. It was a seed of an idea, not yet fully grown into the majestic tree of quantum theory. But the seed was planted. Shortly after that pivotal presentation, in a paper published in the esteemed Annalen der Physik, Planck introduced a constant, a fundamental number that would forever be. His name, h. He termed this h the quantum of action, or Elementas Wirkungsquantum, in German. This constant, the Planck constant, is now recognized as one of the most fundamental constants of nature. It's a tiny number, incredibly small, but its significance is immeasurable. It represents the fundamental scale at which quantum effects become significant. It's the numerical value that tells us just how small these discrete packets of energy and action actually are. In that same paper, Planck also reported more precise values for the elementary charge and the Avogadro-Laszlo number, deepening our understanding of the atomic world. Planck's theory, initially conceived as a mathematical fix, proved to be far more. Its implications were staggering, gradually revealing a universe far stranger and more beautiful than previously imagined. His revolutionary insights were eventually validated by subsequent experiments and theories, solidifying his place in history. For his groundbreaking discovery of energy quanta, Max Planck was deservedly awarded the Nobel Prize in Physics in 1918. He had, almost inadvertently, opened a new window into the very heart of existence. The story, however, did not end with Planck. The torch was carried forward by another brilliant mind, Albert Einstein. In 1905, a truly remarkable year for him, Einstein took Planck's radical idea and pushed it further, applying it to light itself. While Planck initially considered the quantization of energy an attribute of the oscillators emitting the radiation, Einstein made the bold suggestion that electromagnetic radiation itself, light, actually exists in spatially localized packets. He called these packets quanta of light, or Licht quanta. We, of course, know them today as photons. This was a profound leap. Einstein wasn't just saying that energy comes in discrete amounts when emitted or absorbed. He was saying that light is these discrete amounts. Light itself is composed of individual particles, or packets, even though it also exhibits wave-like properties. This revolutionary dual nature, light behaving as both a wave and a particle, is a cornerstone of quantum mechanics and often one of its most bewildering yet elegant aspects. Einstein was able to use this audacious hypothesis to elegantly recast Planck's treatment of the blackbody problem, providing an even clearer and more robust explanation. But his insight went further. It beautifully explained the voltages observed in Philip Leonard's experiments on the photoelectric effect. This phenomenon, where electrons are ejected from a metal surface when light shines on it, had also puzzled physicists. Classical wave theory of light could not explain why the energy of the ejected electrons depended only on the frequency of the light, not its intensity. If light were purely a wave, more intense light, a larger wave, should impart more energy. But this wasn't what happened. Einstein's quantum hypothesis provided the perfect answer. Each light quantum, photon, carries an amount of energy proportional to its frequency, h nu, where h is Planck's constant and nu is the frequency. So, only photons with enough energy, a high enough frequency, could knock an electron free. More intense light simply meant more photons, not more energetic photons. It would eject more electrons, but each electron would still have the same energy, corresponding to the energy of a single photon of that specific frequency. This elegant explanation was another powerful validation of the quantum idea, moving it from a mathematical trick to a fundamental description of reality. Shortly thereafter, the term, energy quantum, was widely adopted for this quantity, h nu. So, while quantization was first unveiled in the realm of electromagnetic radiation, its principles describe a fundamental aspect of energy that is not at all restricted to photons or light. It permeates the very fabric of existence. It tells us that the universe is not infinitely smooth and malleable at its deepest levels, but rather possesses an underlying granularity, a fundamental pixelation, if you will. This revelation forces us to reconsider our classical, Newtonian view of a continuous, deterministic world. Philosophically, this idea of discreteness has profound implications. For centuries, thinkers wrestled with the concept of continuity. From Zeno's paradoxes of motion, suggesting that motion is impossible if space is infinitely divisible. To the smooth flow of time, our intuition has always leaned towards an unbroken, continuous reality. Quantum mechanics challenges this deep-seated belief. It suggests that at the quantum scale, reality is not a smooth gradient but a series of distinct steps. What does this mean for our perception of space and time? Could they too, at some unimaginably tiny scale, be quantized? The idea of quantum geometry hints at such possibilities, exploring whether even the very structure of spacetime is woven from discrete elements. This quantum worldview paints a picture of a universe where interactions are not continuous exchanges but rather discrete transactions, like a digital conversation built from a stream of individual bits of information. Every time an atom absorbs light, every time an electron shifts its energy level, it's a perfectly defined, individual quantum event. This inherent lumpiness of reality at the smallest scales gives rise to the incredible precision and stability we observe in the macroscopic world. It's the reason why chemical reactions happen in specific ways, why certain elements combine only in precise ratios, and ultimately, why life itself, with its intricate molecular structures, can exist and thrive. Think about the sheer elegance of this. The universe, in its wisdom, has found a way to build immense complexity and enduring stability from these fundamental, irreducible packets. It's a testament to the power of underlying rules, of specific, allowed states, rather than an infinite spectrum of possibilities. This limitation, this quantization, is what provides structure and order. It's like building with Lego bricks. You can create an infinite variety of forms, but you're always working with the fundamental, discrete units of the bricks themselves. As we drift deeper into this understanding, let the strangeness and beauty of the quantum world wash over you. It's a world where certainty gives way to probability, where particles can behave like waves, and waves like particles, and where the very act of observation can seem to influence reality. These are further mysteries within the quantum realm, but they all stem from this fundamental idea of quantization, the understanding that the universe is built from definite, discrete units, rather than an endless continuum. The journey into quantum mechanics is an invitation to expand our minds beyond the familiar, to embrace a reality that is far more nuanced and astonishing than our everyday senses might suggest. It's a gentle reminder that there is always more to discover, more layers to peel back from the cosmic onion, and that even the most fundamental aspects of our existence are woven from threads of profound simplicity and elegant complexity. As you prepare for sleep, allow these thoughts to settle softly within you. The world around you, the air you breathe, the warmth of your bed, all are expressions of these fundamental quantum principles, silently at work, orchestrating the stability and beauty of existence. There is a deep comfort in knowing that beneath the apparent fluidity of life, there lies an exquisite, precise, and quantized order. So rest now, dear friend, knowing that the universe, in all its vastness and all its minuteness, is a place of profound order, built upon these fundamental, indivisible steps. Let your mind relax into the understanding that everything is, in its own way, perfectly defined and held in place by the gentle, unwavering hand of the quantum. Sleep deeply, and may your dreams be filled with the quiet wonder of existence. Good night.